second exercise about Taylor series. Again, we also want to calculate the radius of convergence. Well, now this time the function given is the square root, as you see here, the square root of the quantity 1 plus x. As most times, we consider this at x null equals 0 again. We want to find the Taylor series and then determine the convergence radius. Now, let's put this in the usual form, potency, a power expression. You all know that the square root corresponds to an exponent of 1/2. So I have 1 plus x in parentheses power 1/2. And then I take the first prime, the first derivative, f prime of x equals exponent gets factor 1/2 times expression, and exponent is reduced by 1. So I get negative 1/2 as an exponent. And we also know that this negative sign here means something about, or is the same as performing a reciprocal operation. But it does not make sense to change notation now, because we have to proceed, of course. Yeah. And also don't forget, we should have used the chain rule, but since the inner expression has a constant derivative of 1, we do not have to differentiate again, right? Or to perform a correction. So it stays what it is. Then f double prime of x, we get this negative factor here, negative 1/2 times 1/2, which remains, times expression, and now already the exponent gets negative 3/2, reducing it by 1 every time. Well, it's not so easy to find a simple scheme this time. That makes this exercise a little, well, let's say not so convenient as before. Now, f triple prime of x equals next factor, negative 3/2, but now you see, since I already have a negative sign, the whole chain of factors gets positive, so I just leave it away. I have 3/2 times 1/2 times 1/2 times expression, power negative 5/2. One more step to find a scheme, hopefully. It gets negative again. We have factors of 5/2 times 3/2 times 1/2 times 1/2. Still our parentheses term 1 plus x, and then power negative 7/2, and so it goes on. Now, what's the scheme that's most important to this end? Well, first of all, it makes sense now to insert our x null value, which is 0. So we take all these derivatives at x equals 0. Even the function itself, of course, don't forget it, f of 0 equals, and then if I have 0 for x, of course, the parentheses term gets equal to 1. So I have f0 equals 1 power 1/2, which is square root of 1. The positive square root of 1 equals 1. And the first derivative, it's nice to know that all these power expressions get a neutral, result to a neutral value of 1. So we just have to consider these factors from now on. You see here 1 power negative 1/2. It's the same as, by the way, it's 1 over square root of 1, so it's 1, and it stays 1 with all the other expressions. So we have a total factor of 1/2 here. Here we have negative 1/2 times 1/2, which is negative 1/4. Then it's this time I decided to actually to contract these factors, although I'm trying to find a scheme. Sometimes this is a good idea. You can try both ways. And as you see, this is 3, and 2 times 2 times 2 is 8. So I have 3 over 8 here as a factor, positive. And the next one will be, obviously, what do we have? 5 times 3, which is 15 in the numerator. And this is quite simple. This seems to be a simple power of 2 every time. So this time it's 2 power 4, which is 16, and it's negative. So try yourself. We have 1, 1/2. Don't, let's just disregard the sign for a moment. 1, 1/2, 1/4, 3/8, 15/16. It seems that in the numerator, we are constructing sort of products of odd numbers. This is just a, well, you could say a conjecture now, okay, or a hypothesis. 1, 1, still 1, but then 1 times 3, and then 1 times 3 times 5, which is 50. I mean, I just look here and I remember where these odd numbers came from. So it's a fact that they are multiplied. And it takes a while for these products to arise, right? Because in the first step, I have just a factor of 1 again, and 1 times 1. So in some way, we should be able to construct this as a scheme. And now this is what I do. So that's in one step. You try and follow. I decided to write down the constant element separately, because otherwise it would be a little tricky to you know what I mean, to include it here. So I just separated it from the others. So since f of 0 equals 1, we know that this must be the constant also in the Taylor series. But then, starting with the linear term, this is what we need. And obviously, we need an artificial sign change, which I construct by using -1 in parentheses power n plus 1. First I tried with power of n, but then I found, okay, since this is the constant, here n equals 1 is the starting term, then I would get a negative sign. Looking here, apart from the pure constant, also the linear coefficient must be positive. So the negative sign comes with the second derivative and with the fourth and so on, with the even derivatives. That's why I use n plus 1 as an exponent. You see that it works. If inserting n equals 1, I have -1 power 2, which is positive 1. And then I have here, this is my, well, it's not the perfect notation, but it should denote that I multiply 1 times next times next times next times 2n minus 3, and this should denote, just with a remark, that I use odd factors only. You could also write 1 times 3 times ... times 2n minus 3, then it's clear that you only use odd factors. And below here, I have 2 power n simply because now in this moment n equals 1, 2 power 1 is 2. This is when I'm here, and in the next step I have 2 power 2, 2 power 3, 2 power 4. So that works fine. And also never forget, here's the Taylor's formula again of Taylor's theorem. You have to divide by n factorial, and that's what I do. And then that's actually the result. It's not very pretty, but it should be possible to determine the convergence radius also. That's what I'm doing now. Well, looking here, that's quite a little bit to decode. Let me just remove these colored lines, and let's look here. What am I doing? The same thing again. I'm using the ratio test version of the convergence radius again. So it's the same thing as here before. Setting, where is it? Nowhere. Sorry. Here, setting this r equals limit k approaching infinity, and then remember coefficient over successor element, coefficient over successor coefficient. And now we have also we have a negative sign, well, either in the numerator or in the denominator. So in the end, there would be a negative sign inside, which by the way, I ignored before. I just ignored it because we have these absolute value signs, you see. So I could just ignore it. The sign does not matter here. Anyway, I put it here. That's the reason is that I always have the ratio of a positive over a negative coefficient, or negative over positive. In the end, it's a negative factor of -1, which disappears in the end when I apply the absolute value operation. Now, what we also have is, looking here, replacing n by k for a moment, we have this product 1 times next times next times next times, then, oh, I used n, that's, sorry. So allow me just this time to replace this by n. Sorry, that was, otherwise I would have to replace all these n's by k's. So that's easier for me. Then it's all right again. I'm using n now instead of k, doesn't matter. Anyway, we have this chain of odd numbers here, multiplication chain, ending with 2n minus 3, that's it. And then we have our 2 power n times n factorial. That's nothing, I just took this over to here. But then I have to divide by the next coefficient. Since fraction divided by fraction is the same as fraction times inverted fraction, I use the inverted fraction for the next coefficient, right? And so I have to increment n by 1 now to this end. So I get my product of odd factors in the denominator this time, and it goes one step further. And the next odd number after 2n minus 3 is, of course, 2n minus 1. That's what I'm putting here. I can also replace n by n plus 1 again. Then I have 2n plus 2 minus 3 equals 2n minus 1. That's the next factor. I have the next power of 2, which is 2 power n plus 1, which in the end stays in the numerator. You know why? I'm using the inverted fraction. And I have the factorial of the next number, which is n plus 1 factorial. And now I can cross quite a lot of these contributions out. Look here. Oh, now I forgot. I lost my, yeah, well, I should do it this way. Just a second. Moment. Now, again, correcting for this, using n instead. Let's look together. We have the whole chain of multiplications here disappearing because all these factors are also contained here, and even one more factor, which is the highest of all, and that's the one that remains, 2n minus 1. Then what do we have? Yes, we have our powers of 2 power n here, 2 power n plus 1 here. So this is, of course, this is the same thing, but multiplied by 2. You can also, if you want, you can transform it to 2 power n times 2 power 1. Anyway, you can cross everything out except for a factor of 2 in the numerator. This is an additional factor that stays here. Okay, I did it this way. I crossed this out, and then I crossed this out, so it's 2 power 1 remaining, which is 2. Also, I have factorial of n plus 1 over factorial of n. All these factors are contained here. I can cross them out, and I can cross the exclamation sign, the factorial sign out, except for the biggest factor, n plus 1, which remains here. So carefully taking together everything that remains, we have 2 times this parenthesis, which is then 2n plus 2, okay, over 2n minus 1. And that's nice because this is an even number, this is an odd number, but anyway, this is sort of, as we've often seen it before, sort of, you could say, rational term with using our index n, our auxiliary variable, you could say, our integer variable n. So, as you know, since the order or the grade of the numerator and denominator term are the same, both are of grade 1 linear terms, we can just take the ratio of the leading coefficients, which is 2 over 2, which is 1. There are other methods. Also, you can reduce this fraction in some way. You can do whatever you want. In the end, it's you could say the reason for this is that you can neglect these constants for very large values of n. So in the end, the whole expression approaches 1. This is its limit, and that's why also it's the convergence radius of this series. That's, by the way, that's much smaller than before for the other functions, the other examples, but it's quite frequent. There are many cases where we have a rather small interval of convergence, which does not mean that this Taylor series is of lesser value. If you just look here, it's quite interesting to look at the behavior of such a function in the neighborhood of 0, even if this neighborhood extends only plus or minus 1 away from 0. By the way, if I take x equals a -1, which is one of the left side border of this convergence interval, I have square root of 0, and for even lesser values of x, this would no more be defined. It's quite interesting that often, also for a logarithm and things like that, the Taylor series has a convergence radius which is compatible with the definition, as you could say, with the domain of the given function. So you could say it's restricted by the function itself because it's no more defined outside of this convergence interval, at least on one side of it. In this case, the problem appears only on the left side, but anyway, the convergence radius is symmetric due to the construction of such a power series. So it's quite interesting. And by the way, I did not ask you, and I myself, I didn't regard the domain of this function to be restricted. This had no influence on the calculation of this series. So that's our result, and then it's done.